Ben Grant, Z5360919. Kepler's first law is the law of elliptical orbits. Once presumed to be circular orbits, Kepler described the planetary orbits as ellipses with the star placed at one of the foci of the ellipse. This helps explain the concepts of perihelion and aphelion, where the orbiting body is at varying distances to the star throughout the orbit with a minimum and maximum. In practice, the ellipses of the orbital path have very low eccentricity, making them appear circular. Kepler's second law describes the velocity at which planets orbit around their star. In a symmetrical circular orbit, there would be no reason for varying velocities. However, in the revised ellipse model, angular momentum must be conserved. This results in the velocity changing as the distance from the star changes. When the orbiting body is closest to the Sun, the velocity is greatest, and vice versa. A good visualization of this is that orbiting bodies will sweep out equal areas of the orbit for the same time period, irrespective of their location around the orbit. The third law is referred to as the law of harmonies. This law provides a relationship between the orbital period and the semi-major axis of an orbiting body. The square of the period is proportional to the cube of the semi-major axis, which can be seen here. This means that for our solar system, if you divide each planet's orbit period squared by their semi-major axis cubed, you would get the same value. Now we will look at the planet and moon scenario. In this model, the planet does move whilst the moon orbits. This is because each of the bodies are exerting the same gravitational force on each other, and thus orbit the barycenter. The planet's mass is far greater than the moon's, causing a great discrepancy in apparent movement. However, no matter how massive the planet is, it would still experience some level of movement. In question 1, the center of mass is inside the Sun due to its enormous mass. In question 4, the planet's mass has been doubled. This will mean the barycenter is slightly closer to the planet than in question 1, but likely still inside the Sun. In question 7, the mass of the Sun has increased, thus pulling the barycenter back closer to the center of the Sun, yet not quite at the center, which is impossible. In the planet-moon system, the bodies' mass are more similar to each other than the Sun-planet system. This means that the barycenter is closer to the middle of the two bodies. Thus, the Earth experiences a more visible wiggle than the Sun in a Sun-planet system. The red line shown is equal to roughly half an astronomical unit. This is because two grid squares in the distance between the Sun and the Earth, which represents 1 astronomical unit. These figures do not support Kepler's laws. This is because the orbital distance measured from the Sun is not equal to the semi-major axis. The orbital speed of an orbiting body is given by the square root of gm/r, seen below. The speed is proportional to the inverse root of the radius from the Sun. Thus, the closest planet Mercury would be the fastest and the furthest planet Neptune would be the slowest. This happens as the gravitational force between the Sun and a planet is inversely proportional to the square root of the radius, as seen below. Thus, the force decreases rapidly the further away from the Sun, even if the mass increases, as that relationship is linear.